How we are using all of these equations? So we will figure out all of these things by solving this example. So this example says we have boiler of a refrigerator. If you remember, how many components we have in refrigerators? Do you remember chapter 5? Anyone remember these thermodynamic cycles? 4. So the basic thing is we have minimum 4 components, okay? The boiler of a refrigerator is designed to operate at this temperature, 263, assuming we have the refrigerant is frame 22 in the liquid and vapor phase, can be described by van der Waals equation of a state. And here he makes it easy. This is the value of parameter A, this is the value of parameter B. Calculate the vapor pressure at this temperature. So again, the temperature is given. What is the vapor pressure corresponding to this temperature? So the whole idea, what you will do, substitute in fugacity expression. How many times? 2 times. Calculate fugacity of vapor, calculate fugacity of liquid. The pressure value that will give you equal fugacities, so this will be the vapor pressure at this temperature. So always keep this idea of these problems in your mind. Okay? Okay, so how we can solve this equation? So let's start with putting the general expression of fugacity after we substitute with van der Waals equation of a state. So we have ln fugacity divided by pressure. This equal to z minus 1 minus ln z plus ln of molar volume minus B minus A divided by molar volume RT. Okay. So what is the given information we have? We have the value of A. This is given in the SI system. We have the value of B. This is also given in the SI system. We have temperature. This is given 263.71 Kelvin. This is the temperature at which I need to calculate the saturation pressure. So here in this one, in order to solve this problem, so the whole idea of this problem is you will assume saturation pressure value. Okay, this is the first step. I will assume the value of the saturation pressure. Then use the value of the saturation pressure that you assumed plus the given information like temperature, parameter A, parameter B, all of these given information to calculate fugacity for the liquid phase and fugacity for the vapor phase. And if fugacity of the liquid equal fugacity of the vapor, then this means you have correct assumption. But if fugacity of liquid not equal fugacity of vapor, then this means we have wrong assumption and assume a new value, a new P saturation value, and keep your trial and error. Is the idea clear? Okay. So now let's assume my saturation pressure is 68.94 kilopascal. Okay. So the first step is we need to substitute in van der Waals equation of a state. So we have van der Waals equation of a state. It says pressure equal V over V minus B minus A over V square. So this is the van der Waals equation of a state. Okay, I have the value of A given. I have the value of B given. I have this pressure, the value that I assumed, 68.94 times 10 to the power 3. And why I'm using this 10 to the power 3? To convert kilopascal to Pascal, to have everything in the SI system, to be consistent with the value of given A and B. Okay, so what is the unknown we have in this example? Molar volume. Usually this van der Waals cubic equation of a state. So how many molar volume I will get? 3 values. Okay, which one I will pick? Actually, I will pick 2 values, not only 1 value. I will pick the smallest value and I will assign this value to be the molar volume of the liquid phase, and this is the value I will use to calculate fugacity of the liquid. And the largest value, this will be the molar of the vapor, I will use it to calculate fugacity of the vapor. So since we are having this one, so by solving, the van der Waals equation of state, then we have lowest value this will be molar volume of the liquid 0.1394 meter cube per mole. Largest value this will be the molar volume of vapor, and this will be 31.42 meter cube per mole. If you check the fugacity equation, also we have compressibility factor, right? And again, compressibility factor, it has 2 values, one for liquid, one for vapor. So we have another form of van der Waals equation of a state. So we have another form of van der Waals equation of a state containing the compressibility factor Z. So equation of a state says Z is V over V minus B minus A over V RT. So again, this is also van der Waals equation of a state. These are the 2 forms of van der Waals equation of a state. One with compressibility factor, one without compressibility factor. So for this equation here, I have the value of A, I have the value of B. Ideal gas constant, this is known. Temperature is given, 263. So if I use here, in this molar volume, if I use molar volume of liquid, which is 0.1394, then I will calculate compressibility factor for the liquid. And if I use in this molar volume the value of molar volume of vapor, then I will calculate compressibility factor for the vapor. So again, in this equation, I will substitute 2 times. ABRT, this will be constant, no change in this one. But molar volume, I have two molar volumes, one for liquid, one for vapor. Use the first one for liquid, substitute, calculate compressibility factor for liquid. Use the molar volume of vapor to find compressibility factor of vapor. And if we find this one, then I will have compressibility factor of liquid. So this will be 0.004571. And compressibility factor of vapor, this will be 0.9876. So again, till now, I didn't use the fugacity expression. I just using the equation of the state he mentioned in the problem in order to find the variables, the value of the variables or the parameters that exist in the fugacity expression. And since I will substitute in this equation one for liquid, one for vapor, so I need to calculate molar volume of liquid, compressibility factor of liquid. Molar volume of vapor, compressibility factor of vapor. Now, use the compressibility factor, use the molar volume, and go substitute in the fugacity expression. So now, here we will substitute in fugacity expression and we will substitute twice. The first one, I will use molar volume of liquid. I will use compressibility factor of liquid, substitute in the equation in order to calculate fugacity of liquids. And if you do this, fugacity of liquid will be 605.5, and the units is the same as pressure, kilopascal. Second time, I will use molar volume of vapor, fugacity of vapor, compressibility factor of vapor, in order to calculate fugacity of vapor, and this will be 68.09 kilopascal. So since the fugacity of liquid not equal fugacity of vapor, then P saturation cannot be equal to the one we assumed in the beginning, which is 68.94 kilopascal. And I need to go with another assumption, repeat the calculations one more time. Clear? So if you continue making this assumption, you will end up with this table. So this is the table we have in the textbook. So this table gives you the temperature. The first column is the temperature. And in this problem, there is no change in the temperature. All temperature values are the same. Okay, and you have pressure, and these values are assumed. This one, this is what we solved right now, okay? So for each of this pressure value, I will calculate molar volume of liquid, molar volume of vapor, compressibility factor of liquid, compressibility factor of vapor. And then I will calculate fugacity of liquid, fugacity of vapor. They are not equal, so this means phase equilibrium does not exist, and only one phase will exist at this condition. And which phase will exist? The phase that has the lower fugacity. So here fugacity of vapor less than fugacity of liquid, so I will have vapor phase. Okay, let's assume the last one. I will assume the pressure is 758. Again, repeat the same calculation, calculate fugacity of liquid, fugacity of vapor, they are not the same. So this means only one phase will exist, not two phases. And which phase will exist? The phase with the lowest fugacity. So here I will have liquid, because liquid, it has the lowest fugacity. Here I have vapor, because vapor I have the lowest fugacity here. Okay? So always here they have the phase exists, this is the phase with lower fugacity. because the process is moving from high fugacity to low fugacity. So this is the the stable case, similar to molar Gibbs free energy. Okay, so if you compare to this until you find this one, so at this condition, you see here I have fugacity of liquid, here I have fugacity of vapor. Once we have equal fugacity, so this means phase equilibrium exists. I have two phases at this condition, and this will be the value of saturation pressure corresponding to this temperature.